So in summary, the one-time pad, in our example, we're using the Caesar cipher, but we're changing the key for every plaintext letter. And compared to the Vigenère cipher, the one-time pad requires the user to choose a key which is the same length as the plaintext and random. And if we do that, the one-time pad is called unconditionally secure, unbreakable, including unbreakable from a brute force attack. And it's unbreakable from a brute force attack because it's highly likely that with two different keys, or we try a brute force attack, we'll get many possible plaintext messages that make sense. If I get many plaintext messages that make sense, I have no way to know which one's the correct one. So let's go back a few slides and look at what do we mean by unconditionally secure. Where's my mouse gone? There it is. Going back. Just jump back to our attacks on ciphers. We said before the goal of the attacker is to find the key or the plaintext. If we find the key, both are good, both are successful. Finding the key allows us to find any plaintext. We assume the attacker knows the ciphertext. They know the algorithm being used. So we assume the attacker knows we're using the Vigenère cipher, or they know we're using the Playfair cipher, and they know we're using a special character of X. The reason we assume that the attacker knows the algorithm is because it's quite hard to keep the algorithm secret. The algorithm must be implemented in software or hardware, and it's usually available for the attacker to get access to, or to at least predict what it will be. So in terms of security, we analyze assuming the algorithm is public, it's open. And in practice, we'll also, in some types of attacks, assume that the attacker can discover pairs of past plaintext and ciphertext. That is, I don't know the key being used, but I know in the past this pair of users encrypted some plaintext and produced this ciphertext. And that will come up in real attacks on ciphers. Often they assume that the attacker somehow can discover old plaintext ciphertext pairs. And that may make it easier for the attacker. And we're classified between two types of attacks: a brute force attack, try all possible keys; cryptanalysis, try to be a little bit smarter and try to use the knowledge of how the algorithm works, how the plaintext is structured to derive the key or plaintext. Brute force attack involves trying all possible keys. We talk about the key space, the total set of possible keys. When we look at real ciphers, we'll assume that a key is chosen randomly. When we choose a key for real ciphers, we will not choose from a dictionary, we'll choose randomly. And therefore, the attacker, when they do a brute force attack, must try all possible keys. And if we look at binary keys, keys made up of a set of bits, if we say that there's a k-bit key, then it requires 2 to the power of k operations to try all possible keys, where the operations encrypt or decrypt operations. That is, as the attacker, what I do is I try the first key and I decrypt with the first key. I get a plain text. Does it make sense? No. Try the next key. Decrypt with the next key. Does it make sense? No. Eventually we get there, a plain text that makes sense. So the number of decrypt operations is a measure of performance there. And that depends on the number of keys I need to try. And of course, it also depends upon your computer speed. When we look at attacking ciphers, we will not do it by hand. We'll use a computer to do the decryption. So the time to do a brute force attack depends upon how long is the key, how large is the key space, and how fast is my computer to do the decryption. The decryption operation is usually the slowest of the operations. How fast are computers to do decryption? Anyone want to guess? How many decryptions can your computer do of a current cipher? Well, it depends. All right? My phone is much slower than my laptop. My laptop is much slower than my desktop. My desktop is much slower than a network of computers where I have multiple doing decryption, which may be much slower than a set of supercomputers. So the first point, computer speeds vary. Okay, we cannot easily say it will be this particular speed, but we can often estimate what's the upper limit based upon current technologies and have approximations of how many decryptions we can do per second. It depends upon the hardware in most cases, hardware and software. That is the decryption algorithm, the implementation of the algorithm, and the hardware you have, the CPU, the memory, and as you know, there are many combinations, so it's hard to say there's one number for decryption speed. Maybe not today. In another lecture, I'll give you some examples. We'll do some decryptions with real ciphers on my computer, and I'll show you some numbers. But often, I think we'll see those examples, maybe hundreds of millions or tens of millions decrypts per second. So a normal computer may do tens of millions decryptions per second. That's the order of magnitude we're talking about. If I had access to every computer in SIT, I took over all the labs. Maybe I have 1,000 lab computers all decrypting at the same time. Then instead of 10 million decryptions per second, I can do multiply by 1,000. Have each computer doing it. I now have 10 billion decryptions per second. If I could get access to many more computers, I'd increase that, or many more faster computers. We may be talking about billions, hundreds of billions decryptions per second. So to defend against a brute force attack, the key length must be long enough, or the key space must be large enough such that if I have these billions of decryptions per second, it would take me too long to find the key. And some examples are given here. In this table, on the first column, I give the key length. And here we're looking at bits. All right? If we look at English letters, we could convert those English letters to bits. But we'll see in real ciphers, we usually use binary values. For example, if my key length is 32 bits, I choose a random 32-bit value, then there are 2 to the power of 32 possible values. So we say the key space is 2 to the power of 32. How long does it take me to try all 2 to the power of 32 keys? Well, 2 to the power of 32 is about 4 billion. So it's about 4 billion keys. If I could do 1 billion per second with my computer, if that was my computer speed, then the worst case, if I have to try all possible keys, it takes me 4 seconds. If I can decrypt 1 billion times per second, and I need to try 4 billion, it takes me 4 seconds to find the key. If my computer is faster, or I have 1,000 computers of my speed, and in total we can do 10 to the power of 12 decryptions per second, 1,000 times faster than the previous one, then it will take 1,000 times less time, 4 milliseconds. If we go up 10 to the power of 15, a million or 1,000 billion decrypts per second, 4 microseconds. In any case, too short. That is 4 seconds. An attacker is willing to wait for 4 seconds to get the key. In other words, a key length of 32 bits is not secure against a brute force attack. It's easy to break. It's easy to find the key. Now, roughly, current computers are in this order of magnitude, billions of times per second. But you could imagine in the future with dedicated hardware, or if a government had access to many computers, then they may be approaching the far right column. So when we look at key length, we want to consider the extreme cases. One of the first real cipher that was very popular the data encryption standard, we'll see in a later topic, or the next topic, used a key length of effectively 56 bits. And if we had my computer, it may take a few years to do a brute force attack, but people create a dedicated hardware dedicated to doing the decryption much faster, and it can be broken in a matter of hours today. So 56 bits is not enough. Many encryption ciphers today use a key length of 128 bits and even recommend 256 bits. So the secret key is up to 256 bits long. With 128, even if we have this 1,000 billion decrypts per second, it takes us 10 to the power of 16 years. Okay? The age of the universe is about 10 to the power of 10 years. So we start our brute force attack, we must wait for the universe to end to get the result. So most attackers aren't prepared to wait that long. So we say this key length is secure, practically secure. It's good enough for us. In theory, they'll get there. In practice, not within reasonable time. Now, these are just approximate numbers, but you can see even if we take a faster computer, 1,000 times faster, it doesn't save the attacker much time. They still won't get it before the end of the universe. So just increase the key length to defeat a brute force attack. The one at the bottom is not a key length in bits. This refers to the key space of our monoalphabetic cipher. If we have 26 factorial combinations for the monoalphabetic cipher, it would take 10,000 years in this case. If you look through the example, you see I break it in about 1 hour using frequency analysis. So brute force attack not possible, but using cryptanalysis possible. Because we don't have a set standard for the speed of computers, we normally compare algorithms based upon their key length. So I say key length of 128 bits is better than a key length of 64. We compare based upon the key length, not based upon the time, because the time depends upon computer speed. Note they are the worst case times. Worst case involves trying all possible keys. Best case, you try one possible key. Average case, you try half. Okay, so average case, you can divide those numbers by 2. Still doesn't change much when we're talking about 10 to the power of 22 years. Divide by 2 doesn't help the attacker. So it's easy to defend against brute force attacks, make the key longer. What's the problem with making the key longer? It's more secure, but we must get it to the other person somehow. Right? It's how to get that key to the other side is one issue. The longer it is, the more we need to transfer to that person in a secret manner. If it's across a network, there's more network overhead. If we need to remember or store that key, it takes up more space, more to record the value of the key. But in terms of 128 bits, 256 bits, not much difference. They're not very long in terms of what we'd need to send across a network. With real algorithms, usually the longer the key, the slower the algorithm is to decrypt and encrypt. So that's another issue. We would like to encrypt our data fast, so we don't have to wait for the encryption to take place. We've used examples looking at English language. Now we're talking about bits. Right? Our computers will do encryption using binary, but our simple classical ciphers, we can use English as an example. We can convert English to bits by using, say, the ASCII encoding. Take a letter A and map it to an 8-bit or 7-bit value. So there are ways to map our characters into bits. with respect to cryptanalysis, there are different approaches for doing that. So the idea, find weaknesses in the algorithms. We've seen some in the Playfair cipher, the monoalphabetic cipher, that the weaknesses depend upon the frequency of letters. In real ciphers, it's much more complex than that. And we don't get time to go into detail of all the real ciphers or all of the attacks, but you may come across different methods. Linear and differential cryptanalysis we may mention in a later topic. We will see an example of a meet in the middle attack. We'll see one example of that. A side channel attack is using some outside information to help the attack. One of them, I think I mentioned last week, one of the side channel attacks is to, when your computer or someone's computer is decrypting, is to listen to the CPU as it decrypts. So pick up the audio that comes out from your computer. Some of that audio is influenced by your CPU operations. And from that, there are attacks that can try and discover the key being used. When you decrypt using one key, your CPU makes one sound. When you decrypt with a different key, your CPU makes a different sound. And they listen into the sounds, very, very quiet, of course, and they extract the sound that the CPU makes from the other noise and use that to help their attack. So they're using extra information where you say they're using the side channel, not the communications channel. There are many different attacks, though. There's not just one. The way that we measure these types of attacks is in terms of number of operations. The way that we measure brute force attack was the number of decrypt operations, depending upon the key length. Similar here. How many decrypt operations does it take to perform an attack? If it's less than brute force, then that's a good attack. All right? If I have a new attack method and it takes more operations than a brute force attack, then it's not very useful. I might as well just do a brute force attack. But if my new attack method is less operations than a brute force attack, it may be useful. But most of the attack algorithms also use some storage to perform the attack, to do the operations. So the amount of storage or memory they use is important. The more memory they use, the worse the attack. And they may make assumptions about known plaintext and ciphertext. The more they use, the worse the attack. The next slide, I think, talks a bit more about what's known. But for today, I think we'll skip that. And, sorry, this slide. We'll return to this when we look at some real ciphers and talk about different types of attacks. Let's continue with our classical easy ciphers for now. Last thing. The one-time pad we say is unconditionally secure. The one-time pad is the only known algorithm such that there's no way to break it. Under no conditions can it be broken. There's not enough information in the ciphertext for the attacker to find out the plaintext or the key. There are no other ciphers that have this property that we know of. The one-time pad does. So in that sense, the one-time pad is the best cipher in terms of security. The problem with the one-time pad is it's very inconvenient to use. We need a very long random key. Getting that long random key, generating a long random key is hard. We have a topic on pseudo-random numbers. It is hard to generate random numbers, large sets of random numbers. And it's hard to send that key to someone else without it being compromised. So one-time pad is the best in terms of security, but very bad in terms of convenience. So if we can't have unconditional security, we will accept maybe slightly less security. We say computationally secure. And we say an algorithm or a cipher is computationally secure if one of the two conditions are met here. The cost for an attacker to break the cipher, to defeat it, is more than the value of the information they get out from defeating that cipher. For example, my bank account has 1 million baht in it, okay? And it's encrypted, so the password to access my bank account is encrypted with an algorithm. And you know the algorithm, you know the ciphertext for the password. So if you can find the password, the plain text, you can get 1 million baht. That's the value of defeating the cipher. Now, so you want to get that 1 million baht. So what you do is you go and buy a supercomputer which costs you 3 million baht, and you decrypt and you get the key. Okay, so you get my bank account. That is computationally secure in that case because the value to use was 1 million baht, but it cost you more than 1 million baht. You lost money to get that. So I would say that cipher that I used there was secure because it's not worth it for you to break it. The other case, the time required to break the cipher exceeds the lifetime of that information. I have the exam for this course and I've sent it to the secretary. She's going to print it out. And you've intercepted the exam, the encrypted exam. Okay? And the exam, when is it? It's in maybe 15 weeks' time, a bit more, 4 or 5 months' time. So you want to decrypt the encrypted exam and get the questions before the exam takes place in 5 months' time. It takes you 12 months using your computer to decrypt, doing a brute force attack. So in that case, the encryption was computationally secure because the lifetime of that information was 5 months. If you obtain the exam questions after you sit the exam, it's of no value to you. So that is another factor in terms of computational security. Either the cost is too much to break it, or the time required to break exceeds the value or the lifetime of the information you obtain. The two examples I gave maybe are easy to see, but in practice it's hard to put a number on those things. How much is information worth? All right, my bank account may be worth a particular value. How much is it worth you to get the exam questions? What's the monetary value? What is the cost of breaking it? It's very hard to predict. How long is information valuable for? In some cases, like the exam, we could set it's valuable for 5 months. Other information may decrease in value over time. So it's very hard to put numbers on these. Hard to estimate the value and lifetime of information, and hard to estimate how often or how much effort is needed to break the cipher. So there's no one definition of computationally secure. But that's the concept at least. Normally, when we compare ciphers, we'll say, given known attacks, how many operations they take to defeat them, and we'll use that a measure of how good a cipher is. If cipher A requires 2 to the power of 100 operations to defeat it, and cipher B requires 2 to the power of 90 operations to defeat it, then we'll say cipher A is better than cipher B. But there's no easy way to compare in some cases. So that's some of the concepts that we've been talking about and some new ones. Let's finish on classical ciphers. One-time pad. Any questions on how to encrypt and decrypt with the one-time pad? Well, use the Vigenère cipher, but have a long random keyword. Any questions on the Vigenère cipher? Well, use the Caesar cipher, but change the key for each letter. And the Caesar cipher is very easy, I think. So we've got the perfect cipher, one-time pad, but it's very inconvenient to use. So what people have tried to do is develop different ciphers that are computationally secure, but easier to use than the one-time pad. And what they do is that they combine some of the techniques we just saw, substitutions, with another operation called transposition. So the next two examples are of transposition ciphers, transposition techniques, and then we'll see in the next topic that real ciphers use a combination of substitutions and transpositions. Substitution, take one letter, take our plain text character, for example, and replace it with another letter from the alphabet. That's what we were doing. There may have been pairs of letters. Transposition, take our plain text characters, rearrange them. So my plain text letters are H-E-L-L-O, just change the order of them. That's a transposition. Mix them up. First example, we'll just go, I think, two examples of transposition ciphers. Rail fence cipher. We take our plain text, we'll use Internet Technologies and Applications, one of my old courses, and we write that in a set of rows where the number of rows is determined by a key, or we call the depth. So for our example, we'll use a depth of 3, meaning we'll write this plain text across 3 rows, and then we'll obtain the ciphertext by reading row by row. Let's do it, and then it'll be clear. So I'm just going to write that Internet Technologies and Applications, but across 3 rows. So INT, Internet, and then we'll go back to row 1, 2, 3, and back to the first row. The number of rows is the key in this case. It will be chosen by the users. Here we choose 3. Now I write it in diagonals because it will be a little bit easier to read and write that way, but it doesn't have to be. You just need 3 rows. Internet Technologies and Applications. Let's finish it off. Internet Technologies and Applications. And what we do to get the ciphertext is simply read the first row, then read the second row and the third row. The ciphertext, I'll write it in lowercase, it's faster. Just read the first row. And then the second row. And the third row. Just squeeze it in. That's AO at the end. Easy. If I had a depth of 4, I'd have 4 rows. Okay. So the depth is the key. The key would be known by the encryptor and decryptor. It's secret from the attacker. Transposition means that the letters in the plain text, the same set of letters, also appear in the ciphertext. It's just rearranged them. How do you break this if you just know the ciphertext? Last 3 letters, what were they? Oh, A, L, A, O. we can still use frequency analysis attacks in this to break this because, again, we expect in most cases the letter E to be the most common in plain text. So the letter E still remains in here. Okay? So there's nothing changed here. But we need to determine the depth. How many rows did the encryptor use? And I'll leave it as an exam question or a quiz question to give you some ciphertext and find the plain text. You'll find it's very easy to do a little bit of trial and error, assuming you know the words that you're looking for. And as a hint, in the quizzes and the exams that we have in this course, unless I say otherwise, all of the examples or questions are in English. And I'm not so mean that I give difficult words as plain text. I usually use plain text words which you will recognise. Right? So if I give you an exam question, here's some ciphertext, find the plain text without the key, you know you are correct when you get a plain text message that makes sense. You'll know you're incorrect if you get some random characters. Right? So I'll try and make it easy from that perspective. Here we could try you could do a bit of a trial and error and try some different depths. A depth of 1 doesn't help. A depth of 2, 3, 4, we could try others. And if you look at some past exams, sometimes I've given such a question where I say the depth or the number of the depth is between 2 and 4. So a trial and error approach could try the 3 depths until you get words that make sense. If we determine that the depth is 3 in this case, what do? If I can determine the depth is 3, or I want to try a depth of 3, given the ciphertext, split it into 3 parts. Where would it be? If we split it into 3 parts, then it would be split into... All right, maybe we can try a quick attack. If we assume the depth was 2, we'd split it into 2 parts, which would be about here. That is, there'll be the first part. A depth of 2 means 2 rows. And the second part. If it was a depth of 2, what would the plain text be? The first letter would be I. The second letter, S. The third letter, E. The next letter, D. E. P. Do you recognise anything yet? Not yet. You could keep trying, but the idea is you need to look for words that make sense. E, C, N. It's not independence. It doesn't make sense, so we may say, well, this depth is wrong. A key of 2 did not work. What about a key of 3? A depth of 3, then we split it into 3 parts. It would be split here, here, into 3 parts. And then we'd read off. The first letter is I, N, T, E, R, N, E, T, and then you realise, Dr. Steve teaches about the internet. It's most likely the correct plain text. Let's keep going with that, and you'll see something that makes sense. Okay. So with some knowledge about what you expect to see, it's not so hard to break such ciphers. Let's try another one, and then we'll see that. So the transpositions on their own are not secure. They're just rearranging letters, and very easy for an attacker to defeat them. But we'll see that they add some key property. Even though they're very simple, they can be useful in real ciphers. Here's the rows columns transposition. We take our plain text, write it as a set of rows where the number of rows is determined by the key. Here we'll choose a key which is, it's not really a number, it's an arrangement of the columns. For example, I'm going to use 6 columns. I choose that, part of the key. So I need 6 numbers here in some, say, random order, 3, 1, 5, 6, 2, 4. And that's going to tell me how to read the matrix as we write it. So let's encrypt secure cryptography with this key of 315624. We write security and cryptography in rows where there will be 6 columns. So I'll actually write the key first. Three, 1, 5, 6, 2, 4. That's my key. So let's write security and cryptography across 6 columns. Cryptography. And for this algorithm, we need to have to fill out our matrix. So we have one element left. So we'll add some padding to the end. Padding is when we have some plain text usually, and our algorithm requires a certain length. In this case, with 6 columns, we must have a multiple of 6 in terms of our length. Our plain text, well, it's not. We need to pad the plain text out such that it is a multiple of 6 characters. So let's add a special character at the end. And as long as the encryptor and decryptor know the special character, we can use anything. But again, in English, it's common to use a character that doesn't occur frequently. I like the letter X. So that just pads out such that we have a multiple of 6 characters in our plain text. This is called a padding character. Now, to encrypt, we read the columns defined by the order of our keyword, our key. That is, the ciphertext is obtained by reading not the first column, but the column numbered 1, EYYA. The column number 1 is EYYA. So that's the first 4 characters of the ciphertext. And now the column labeled 2, think of the second column to read, RDOY. And then column number 3. And I'm just writing in uppercase just so we can distinguish between ciphertext and plaintext. Number 4 is ICGX, 5 CAPP, UNTH. So we obtain the ciphertext in this case. Any questions on encrypting with either the rail fence or the rows columns? Write the plain text in the rows columns, write it row by row, then read the columns where the order we read the columns is defined by key. These examples of classical ciphers are probably best for you to learn by doing them yourself. So we'll not do many more examples in class. In the first quiz, I'll give you some plain text to encrypt or some ciphertext to decrypt, and in doing that, you'll quickly remember how to do the steps. Be aware with decryption. So in the slides, in the examples, I often go through encryption. I don't tell you exactly how to do decryption, so you need to work backwards. Right, so be careful. So when you decrypt something, make sure you get some plain text that makes sense. If you don't, maybe you've done the steps wrong. This is just another rearrangement of our security and cryptography. They're quite easy to attack. It's quite easy to do analysis and try. If we can work out the number of columns, then we can look at expected words. So the transposition techniques on their own are not very good. But there's two principles that they use to illustrate. The first one is that of these operations, transposition and also substitution, one principle used in real ciphers, if you apply the operations multiple times, generally you'll get more secure output. So that's the first one we'll illustrate. But before we do, maybe there's questions on rows, columns. Okay. All right? Okay. So let's look at how can we use the ciphers multiple times to add security. And the next example tries to show that. Let's explain it. So what I've done in this case is I have a plain text. Attack postponed until 2 a.m. XYZ was just some padding at the end. That was my plain text. I had a key, 4312567, and I applied the transposition cipher, the rows columns, the previous one, and this is the ciphertext. You can check that. That's not the point here. We get this ciphertext. And then I use the same key, the same cipher, and encrypt the first set of ciphertext, and we get this second set of ciphertext. I'll show the operations that I did, and then we'll explain the benefit of it. The idea was that we took our plain text, we encrypted using some key, and we got as an output some ciphertext. I'll denote as C1. That was using the rows column cipher. And then we took that ciphertext and encrypted that using the same key in this example, and we get a different ciphertext, C2. The point that we'll try and show is that C2, the ciphertext C2, is more secure than C1. By applying the encryption operation, the transposition operation multiple times, we can make the output more secure. By more secure, we mean that if the attacker has that, it's harder for them to determine the original plaintext. And one thing that we can measure that is we think that the output is more random. The more random the ciphertext, the harder it is for the attacker to work out the original plaintext. So let's see on our example, this is C1, TTNAA, and C2 is this one. Which one is more random? Well, it's hard to see. So, to illustrate, instead of listing the letters, list the positions of those letters. That is, the letter A is the first letter. The letter T is the second. T is the third in attack. A, C, K. So we have the first letter, and because I cannot fit it on one line, I wrap around to the second line, but think of it's on one line. We have 28 letters in the plain text. A, T, T, A, C, K, and so on. So that's the position of the original letters. When we do a transposition, we rearrange those letters. Where did the A go to? When we did the transposition, the A ends up, and it shows here, the first letter, 01, ends up here in the 13th position. If we see that, this A, if you do the encrypt, moves to this position. The second letter, the first T here, moves to the 9th position. This T, if you check, goes here. If you follow the letters from the encryption, you'll see that they change the positions, and the 28th letter ends up at the last position. The 8th letter in the plain text ends up at the 14th position. So that's just the nature of the algorithm. It rearranged in that order. Then if we take that ciphertext, TTNAA, so on, and apply the operation again, we rearrange more, and we get NSCYA. And the first letter from the plaintext, A, in the first position, after the second operation, ends up down here, which is the 22nd position. The second letter of the plaintext ends up, if I can find it, here, the 10th position. So the numbers are just showing the relative to the original plaintext, the first letter, the second letter, third, fourth, and so on. Why do this? Look at the arrangement of numbers after the first transposition. Look at these numbers. Do you see any pattern in them? After the first transposition, do you see some pattern in the numbers? Don't say no. Yes, you see a pattern. 7 is something to do with it. Let's read the numbers. 3, 10, 17, 24. All right, there's something there, isn't there? That they're differing by 7 there. Oh, but the next one doesn't. 4. But 4, 11, 18, 25 differ by 7. There is some pattern in the first ciphertext that comes out, and it's not hard to recognise. We recognise it in a few seconds there if we look at the numbers. The idea is in a ciphertext, to make it secure, it should appear random. No pattern. Here, there's an easily observable pattern, or in some parts of it, so we say it's not so secure. Something's incrementing by 7 every 4 numbers, every 4 characters. And that's related to the algorithm and the key length. If we look at after the second transposition, look for the pattern. The bottom 2 rows of numbers, what pattern can you see? And it may not be just incrementing by a number, it may be some other relationship. What can you see after the second? You need to look closely. See if there's some relationship between the numbers and after the second transition. Numbers differ by some values. Multiply. Can anyone see it? Don't try too hard because I cannot see the pattern, okay? It doesn't look like there's an easy observable pattern there. I would say it looks random. Okay, if you look at that sequence of numbers, well, to me it looks approximately random. Whereas the first sequence, 3, 10, 17, 24, if you tell me this sequence of numbers, I'd say that's not random. There's some pattern in there that I observe. And this is the principle we're trying to illustrate. Applying the same simple cipher, the same simple operation multiple times makes the output more random, more secure. And that's what we use in real ciphers. We take simple operations and repeat them multiple times. And if you keep going, then you jumble up things more, make it more random. What's the problem of applying the same operation multiple times? Here we did it twice. What if I did it 200 times? What's the problem? Our performance may be a problem in that my computer must do this operation. If I do it one time, it takes a short amount of time. If I do it 2 times, it takes twice the amount of time. If I say do it 100 times, then I've increased the time it takes to do the encryption. So with security, we actually, or with cryptography, we care about being secure and being convenient to use. And one measure of convenience is that it performs fast. It performs well. The more operations, often the more secure, but the longer it takes to encrypt. I don't have an example to finish with this, but if you try different ciphers, that is, apply this one and then apply the Caesar cipher and then apply rows, columns again and then Caesar cipher, it would be even better. And that's what real ciphers do. Combine operations of multiple simple ciphers. Questions on substitution or transposition ciphers? One of the harder exam questions I've had is how to decrypt a rows column cipher, which was with Caesar cipher, and there's no key given. You may look at the last year's midterm exam at the end of the handout. You'll see. Any questions?
Then you have to try other methods as well to check if...
Right. Right, so one, yeah.
Even if you have almost double free.
Right. Defeating this becomes harder because if we decrypt the first one, the answer we get is ciphertext. It's partial, it's random already. So it's hard to recognize the patterns. So we need to do 2 steps at a time. Try this one and try that one and see what it is. But that, of course, makes it much harder. Okay, so yes, the multiple operations make it harder for the attacker to work backwards to get the original plaintext. And if you combine, maybe we can draw something like, take your plain text, encrypt with say a rows column cipher, take the output, encrypt with a Vigenère cipher, and try that several times. Multiple, this is a transposition, this is a substitution. then you get some ciphertext. The attacker has this ciphertext and has the challenge, find the plain text. And that's much harder than the examples of attacks that we saw. And that's what real ciphers are built upon. Multiple small operations. What's the time? We have 15 minutes to go. Let's see what we've missed, and then we've got one last example of a classical cipher, I think. We'll cover it next week. We'll look at real ciphers, but the point is we'll see that they're made up of often using substitutions and transpositions. And in fact, there are often names for them. Transpositions are sometimes called permutations. So in real ciphers, the design usually refers to a permutation, we'll see. And substitutions are used. And in real ciphers, you'll see things like S boxes. An S box, a substitution box, where we basically do a simple substitution. And permutations or P boxes. So many ciphers are made up of substitutions and permutations, repeated. But before we get to them, and this is the sort of outside of the encryption techniques we've looked at, another different approach for privacy is called steganography. Instead of encrypting something, hide our plain text in another message. Here's an example. And if you've been in my lecture before, don't tell everyone the answer. Here's a message. Find the hidden message. Here's a message that makes sense. It's been sent from one person to another. It's, say, a letter. And the attacker intercepts this message. It looks like a normal message. I don't even think there's anything hidden in there. How would I know? Well, I know that actually there's a secret message hidden inside this ordinary message. Can anyone find it? So this is the concept of steganography. We hide one message in another. See if you can find the hidden message. Someone's got it already. Right. Someone's got it. Once you see it, it's very easy. Anyone else get it? What are you looking for? What are you looking for? What? Capital letters, okay. So one idea is, do the capital letters in this make some sentence or something that makes sense? D, G, G, O, M. I think if you write them down, maybe it doesn't make much sense, the capital letters. But that was one idea. We could use capitals to hide a message inside this other one. What else can you look for? Maybe first letters of words, but I think you won't find that works. First words of each line. That was the hint, it's not the answer. Maybe look at the end of the lines. The last word of each line. Your package ready, Friday 21st, room 3, please destroy this immediately. All right, so there's the message that was hidden inside this normal looking letter. Okay. So this is steganography. We can communicate a message secretly to someone else. And an advantage of this approach is that when someone sees this, they intercept and see this, they think, well, this is just a normal message. It's not even encrypted. I will not try to decrypt anything. I'll not try to break it. There mustn't be anything hidden in here because it makes sense. So the attacker may not even know that there's something hidden in here. And that's useful sometimes because in some circumstances that encrypted information may be blocked or may be analysed in a much more vigorous way than unencrypted information. So if you don't want to let others know that you're actually encrypting information but still communicate secure messages, then steganography plays a role. But the problem is, once you know the algorithm, it's easy to find the plaintext. So the security of steganography depends upon how secure or how hidden the algorithm is. Right? So if I use this algorithm today, and if I give you another question in the quiz, then you know the algorithm, then it's not going to work very well the second time. Okay? Once you know the algorithm, you'll try that and find the secure message. So I need to use different algorithms if I want to keep using steganography. So it's not very practical in many cases, but it is useful if we want to hide something and we don't want others to know that we're encrypting, that we're hiding something. So hide a real message in a fake message, a fake but meaningful message. Now the receiver must know what algorithm was used for hiding. Other examples, so the old days, you have a written letter on a piece of paper, maybe the idea of invisible ink, or put tiny pinholes above the letters that make up the hidden message, so that when someone holds up the piece of paper to the light, they see the pinholes and they read the letters. So that was one of the old approaches for hiding messages inside normal letters. Today in digital communications, we usually use steganography operating on bits. In a number of applications we use, like image transfer and videos, which is image, multiple images, and audio. With those applications, often we can transfer the data, and even if some of the bits are changed, the receiver can still see or consume the data. That is, I stream a video or I send a video from one location to another. If I change a few of the bits in that video, it'll still play back at the receiver. Okay? You may see a few pixels change colour. You probably wouldn't even observe the changes. So some data transfer are tolerant of changes of the original data. So what they use for steganography is they change certain bits in the original video, send that video. When it plays back, it looks like a normal video. But if you know which bits were changed, then those bits are read and they make up a secret hidden message. The same can be done with images and even audio. I'll show you one example to finish. The advantages of steganography, it doesn't look like you're hiding anything. And that's used today when, say, encrypted communications are blocked. They are blocked by organisations. Then by sending an unencrypted message, you can still send a hidden message. Once you know the algorithm, it's easy to break. The other problem, that can be inefficient. To send a short message, we must send usually a much larger message, inefficient for communications. The example is not so easy to it's not so easy to demonstrate. We'll try. Where? Here's a picture. Okay, so here's the image, a JPEG image. And what I've done is I used some software. So a JPEG image, what is it? A normal image, an uncompressed image, is a sequence of bits where, let's say, every 8 bits represent a colour in a pixel. So this image is made up, this image is made up of 275 pixels across and 183 pixels down. Each pixel is a colour. In this case, very simple, either red, white or blue. And each pixel is represented by a 24-bit number. Three values, red, green and blue. That is 8 bits for the red portion, 8 bits for the green portion and 8 bits for the blue portion. That's one way to encode an image. That is, there's a 24-bit number that says that this pixel is red. There's another value that says this pixel is white. JPEG takes all those bits and does some compression on them to make the file smaller. We can use software to change some of the bits in there, and I've done it. What I've done is I've taken a text message, I've changed using an algorithm some of the bits in there to encode the text message and get a picture that comes out, and the picture that comes out when I change some of the bits is this one. Okay, just be careful. This is the second image. This is the first image. This is the original image. I applied a steganography algorithm and it took a text message and it changed some of the bits in the image and then compressed again with JPEG, and the output was this one. Any difference? Almost no noticeable difference in the image. Okay? Now there's a difference in the size if you look closer, because when it recompressed it used a slightly different algorithm to compress. Right? So that was the limitation here, the file size. But you can overcome that by using a different compression algorithm or a different level on the compression such that it ends up with the exact same file size. Now, what does it do? What was the message? We need software to do that. So the software I use is called Outguess. It just implements simple steganography. If I take the receive message, let's say someone sends that second image to me, the receive message, the second image, I use this software and it applies the reverse of the operation, and let's call it, it produces some output message. What it does is it reads through the image, extracts some bits from there using an algorithm that was used in the initial step, and that was the message encoded in the original message, original image. It's hard to see what the algorithm is doing there, but what I did, take the image, encode this message in it by changing some of the bits, changing the bits such that hopefully the output image doesn't look much different from the original one, send that second image, the receiver decodes, they get the message out, the hidden message, and someone who observed the communications doesn't think that they were securely communicating, thinks it was just an image of a flag being sent. That's the idea with steganography. Questions? Then I think that comes to the end of this topic, this set of slides, and a good time to stop for today. What we'll do next week is look at real ciphers, block ciphers, and see how substitutions and transpositions go together.